Okay, and so we're going to look at question 7. Okay, so question 7, and we can see straight away by looking at it that it is a functions question. So it relates to the future population of 2 different cities. And from just a basic glance at the 2 functions, we can see here that they're going to involve logs and indices. So we can see our indices here, and we are going to have to use those in order to solve these functions. Okay, so the first part of the question then relates to Sapphire City. Okay, and so here I'm asked to find the population. I'm told the population in Sapphire City at the beginning of 2010 is 1,100,000 people, and I'm asked to find the value of S. And so there's a couple of useful pieces of information in our introduction. First of all, it is that the population, the function that relates to Sapphire City is this one here. P of t is equal to S multiplied by e to the power of 0.1t by 10 to the power of 6. And also very interesting and very important for us, we're told at the beginning of 2010. Here we're also told in the question that t is time in years, but t equal to 0 is the beginning of 2010, and both s and k are constants. So that's going to help us to solve for s. So it's just basic substitution as we begin. And so, as always, when I begin a question, I will write down the pieces of information that I'm going to need for that question. So the first part is P of t is equal to S e to the power of 0.1t by 10 to the power of 6. As we said, t is equal to 0, and then the other part is that P of 0 is equal to 1,100,000 people. Now, just because I can see here the function uses scientific notation, I can also see very clearly if I'm to change this to scientific notation, well, that's going to be the same as 1.1 by 10 to the power of, and I'll just count back here, 1, 2, 3, 4, 5, 6. So I have 10 to the power of 6. Okay, and so now I can begin with my basic substitution. So here I'm going to have S, E, 0.1, and instead of t, obviously I'm going to write in t is equal to 0, multiplied by 10 to the power of 6, and that's equal to 1.1 by 10 to the power of 6. So the first thing that I notice in order to make things a little bit easier for myself is I have 10 to the power of 6 here, I have 10 to the power of 6 here. So what can I do? So I can simply divide across by 10 to the power of 6. And so dividing across by 10 to the power of 6, well, that's going to cancel that, and it's also going to cancel that. So now I'm left with, well, 0.1 multiplied by 0, that just simply gives me 0, is equal to 1.1. Going back to our indices, we know that anything to the power of 0 is equal to 1. So a very important rule for us to remember. And that so then basically gives us S. So anything to the power of 0, e to the power of 0 is simply 1. So S times 1 is equal to 1.1, which gives us S is equal to 1.1. And that's question part A solved, and we can rewrite our equation later, our function, which will help us later on in the question. So that equation has now become P of t is equal to 1.1 e to the power of 0.1t by 10 to the power of 6. Okay, so question 2, again it's basic substitution here. It asks us to find the predicted population in Sapphire City at the beginning of 2015. So at the beginning of 2015 we know that's t equal to 5 because 2010 was t equal to 0. And so here I'm finding then P of 5. So I have P of 5 is equal to 1.1 e to the power of 0.1 times 5 multiplied by 10 to the power of 6. So that's 1.1 e to the power of 0.5 by 10 to the power of 6. And on our calculator then, that gives us 1,813,593.398. Now it's population, so I'm just going to round off to the nearest whole number. So here that's 1813593. So that's our population at the beginning of 2015. So that's our answer to question B. Okay, so here in part C, we're asked to find the predicted change in the population during 2015. So here I'm rewriting the function again, and also my solution to part B, P of 5. So that was the population at the beginning of 2015. Now I know if I got the population at the beginning of 2016, that would be the same, would help to give me the change during 2015. I could just subtract the two away from each other. So all I'm looking for here then is P of 6, and that's equal to 1.1 e to the power of 0.1 times 6 multiplied by 10 to the power of 6. And when I substitute that in on my calculator, I get 2,004,330.68. So again, rounding off to a whole number, I have 2,004,331. And so in order to get my population change, well then I'm just going to subtract 2,004,331, and I'm going to take the population at the beginning of 2015 away from that, this 1,800,000. So take away 1,813,593. And so when I subtract those, I get an answer of 190,738. My answer, my solution to part C. Okay, so here in part D, we're asked in relation to Avalon. So I've brought back in the function, the preface, to give us the information in relation to Avalon. So we're told Q of T for Avalon is equal to 3.9 e to the power of kt times 10 to the power of 6. Okay, and in this question we're asked to solve an equation to show that k is equal to minus 0.05. We're told it's the beginning of 2011 and we're told the population at that time. Well, if the beginning of 2010 is t equal to 0, well then we know that at 2011 it's going to be t equal to 1. So that's our first piece of information. So here I'll have t equal to 1, and then I know that q of 1 is equal to 3,709,795. Okay, and so I'm just going to substitute into my formula and solve. Okay, so that's going to give me 3.9 e to the power of k, and that k is times 1, multiplied by 10 to the power of 6 is equal to the 3,709,795. Okay, so just tidying that up, I get 3.9 ek by 10 to the power of 6 is equal to 3,709,795. Now, in order to get e to the power of k, or to get k on its own, well, I know I can get rid of these from here. And how do I get rid of them? Well, I would divide across. So very basically then, if I divide this side by 3.9 by 10 to the power of 6, I would also have to do the same on the other side. So that's 3.9 by 10 to the power of 6. And that cancels that, and that, which leaves me on the left hand side with e to the power of k. And when I divide those in, I get 0.951229487 on my calculator. Okay. Now, so the next piece of information, or how do we solve for k? Well, we're going to have to use our logs. Okay. Okay, so here we have our rule for our logs. So it tells us that for a to the power of x equal to y, that log ay is equal to x, or vice versa. So here we can use our natural log because log e to the base e is our natural log, and we have that on our calculator. So here I'm going to say, well, the natural log of e to the power of k is equal to the natural log of 0.951229487. Now that doesn't really help us all that much until obviously I know that I can bring that k down to here. Okay, so that's my next step. So here I have then, well, k, natural log of e, is equal to the natural log of 0.951229487. Okay, and obviously the natural log of e is 1, it cancels. So that gives me k, and when I put that into my calculator, I get minus 0.0499999, and they've asked me to show it correct to 2 decimal places. So that gives me k is equal to minus 0.05. And so we have shown exactly as we should have, so we can even write our QED down here. Okay, and just for our own sake as well, we can rewrite the function for Avalon City now that we have our answer for k. So that gives me Q of t is equal to 3.9e minus 0.05t by 10 to the power of 6. Okay, so here I'm asked to find the year during which the population in both cities will be equal. So the first thing that I'm going to do, I can and divide across by 10 to the power of 6. So that's going to cancel both of those for us. So that will cancel that and cancel that. So that gives me 1.1 e to the power of 0.1t is equal to 3.9 e to the power of minus 0.05t. Okay, so I want to start just to tidy things up and get things on their own. So the first thing that I'm going to do here, I'm going to divide across by 1.1. So here, if I divide by 1.1, then over here I also divide by 1.1, and they will cancel. So that gives me e to the power of 0.1t is equal to 3.9 e to the power of minus 0.05t over 1.1. Now I want to bring the e's all to one side as well. So on this side, on the right hand side, I am going to divide here by e to the power of minus 0.05t, and so if I do that here, I'll also do that on the other side. So I'm going to have e to the power of minus 0.05t over here, and obviously this and this have cancelled. Okay, and so looking here, well, what do I have? I have something to the power, two things of the same base raised to a power divided by each other. So I'm going to use my rules for indices. Okay, and they say, well, if I have two things of the same base divided by each other, well, then I'm just going to subtract the powers. So that's going to give me e to the power of 0.1t. So I'm subtracting the powers, that's minus, and that's minus 0.05t, and which is equal to 3.9 divided by 1.1. Okay, now minus by minus we know is a plus. Let's write a little plus sign over the two of those there. So that's going to give me e to the power of 0.1 plus 0.05, so that's 0.15t is equal to 3.9 divided by 1.1. Okay, and similarly then to using our rules for logs in part D, we're going to do the exact same here. So here we can say, well, the natural log of e to the power of 0.15t is equal to the natural log of 3.9 divided by 1.1. Now I can bring down that 0.15t, natural log of e is equal to natural log of 3.9 over 1.1. And just moving those over to make a bit more space. I'll draw a line down here like this. Then using our calculator, well, we get, similarly following the same rule as in previous question, that the natural log of e, well, that's just equal to 1, so that's going to cancel in essence. So we're going to have 0.15t is equal to, and the natural log of 3.9 divided by 1.1. So on our calculator that gives us 1.265666373. 6373. So that means that t is going to give us that divided by 0.15, which gives us t is equal to 8.4377. So a t equal to 8. So what year is that during? That's during, which means that it's during 2018. Okay, so during t equal to 8 or during 2018. Either of those will work as our answer. Okay, so here part F, we're asked to find the predicted average population in Avalon from the beginning of 2010 to the beginning of 2025. So what we have here is, well, we have an integral, and so it's the average. So first of all, let me just write down the function for Avalon. So that, okay, so that's q of t is equal to 3.9 e to the power of minus 0.05t by 10 to the power of 6. So we're going to integrate that. So the integral of q of t with respect to time, and that time is from the beginning of 2010 to the beginning of 2025. So we can see that that's a period of 15 years. So our average then is going to be, so 1 over 15 times the integral of t equal to 0 to t equal to 15, the integral of q of t dt with respect to time. Okay, so that gives me the integral then of 1 over 15, the integral from 0 to 15 of 3.9 e to the power of minus 0.05t by 10 to the power of 6 dt. Now here I can see obviously that 3.9 and 10 to the power 6, they're constants, so I can pull those outside the integral, which will give me 3.9 by 10 to the power of 6 over 15 by the integral then of from 0 to 15 of e to the power of minus 0.05t dt. And now I can basically integrate that. And so just as I go about integrating that, well, from our log tables we know that the integral of e to ax, when I integrate that, that gives me the 1 over a times e to the power of ax. So that's going to be our integral that we'll use. So here we have my 3.9 by 10 to the power of 6 over 15, and that's going to be multiplied by our integral here, so that's going to be over minus 1 over 0.05 times e to the power of minus 0.05 t from 0 to 15. Okay, so in integrating this, then I'm going to have 3.9 by 10 to the power of 6 over 15, and then inside my square brackets where I integrate, I'm going to have minus 1 over 0.05 e to the power of minus 0.05, and I substitute in my 15, and that's going to be minus, and again, minus 1 over 0.05 e to the power of minus 0.05 times 0. And as before, we know that anything to the power of 0 is equal to 1, so that will make that a little bit easier for us. So, and in fact, we can just put that straight like that into our calculator. So that gives us 10.55266,895, and so I'm just left then to multiply that by the 3.9 by 10 to the power of 6 and divide it by 15. And so that gives me an answer of 2,743,693.926, and so rounding that off for our predicted average population change, I get 2,743,694, and that's my answer then to part F. Okay, and so finally I'm asked to use the function q of t to find the predicted rate of change, and so I know that rate of change always means differentiation, and that's in Avalon at the beginning of 2018, and so I know from that statement that t is going to be equal to 8. Okay, and so just before I differentiate, well, I know from my log tables that if f of x is equal to e to the power of ax, well then f prime or f dash of x is going to be equal to ae to the ax. Okay, so that's going to be our rule for our differentiation. Okay, and so similarly then, as I did with my integration, I am going to pull out the 3.9 by the 10 to the power 6. So q prime of t or q dash of t is going to be equal to 3.9 by 10 to the power of 6, and then I'm going to differentiate here, so that's going to give me minus 0.05 for my a, and that's going to be e to the power of minus 0.05 t. Okay, and so now I can substitute in for 8. So I'm going to have q prime or q dash of t at t equal to 8 is equal to 3.9 by 10 to the power of 6, bracket, minus 0.05 e to the power of minus 0.05, and instead of t, obviously I'm going to substitute in 8 here, and I can put that straight into my calculator here to work out the predicted rate of change in the population of Avalon at the beginning of 2018. That gives me minus 130,712.409. And so simply just rounding off there, that gives me minus 130,712 as my predicted rate of change of the population of Avalon. So that's my answer to part G, and all I really had to remember there was when I see rate of change, that means I need to differentiate.